this afternoon, which will be about this morning. We saw affine schemes, and the idea of schemes is that those are types that are locally like affine schemes. So I will go make this precise. So a type X is a scheme if there is a finite open cover, we write UI for I in I of X such that for I, UI is an affine scheme. So, okay, so here this is a finite family. So A has to be a finite set, and each of the UI has to be an open subtype of X. So the first remark is that if X is a scheme, then X is a set. So in the sense that its identity type are proposition, and this is just because we have a cover by affine scheme which are sets by definition. So a second remark, which I will not use in this talk, but which is worth mentioning, I feel, is that schemes enjoy Zariski local choice. So here recall that the affine scheme by assumption have this Zariski local choice. And so then we have a finite open cover of X by affine scheme. And so let's say we have a surjective map like this. We have a surjective map like this from the open cover by the UI. For each UI, we have an open cover of the UI such that over each piece of the open, so let's say U11, U1K, an open cover of U1, for example, so that over each piece we have section of P, and then you just get to bundle all these open covers of each part of the open cover as one big open cover. And so, of course, what I want to do is to give example. So, of course, affine scheme are schemes because you can use the trivial cover with only one piece. So let us look at another example. So A2 minus the origin 0 is a scheme. Okay. Let's prove this. So the idea is that we can write this as the type of xy in A1 such that x is different of 0 or y is different of 0. So this is because xy being different of 0 is equivalent to this. And then we want to cover this by pieces, and there is an obvious candidate. So we can use the xy in A2 so that x is different of 0. So this is an open subset, and this is affine because it's actually the spec of Rxy localized at X. And so we have a similar piece with y here and y here, and the two pieces together cover this type because we have that x is different of 0 or y different of 0, so it's always in one of the two pieces. So, okay, so this proves that this is indeed a scheme. Now I want to prove that it is not an affine scheme. So to this I will need a lemma. So we have a map I which goes from A2 minus 0 to A2. So which simply forget the proof that x is different of 0 or y different of 0. And then the map y star that is induced, which goes from R to the A2 to R to the A2 minus 0 is an equivalence. So, okay, and so once I prove this, I have as a corollary that this is not an affine scheme, because if it was affine, then this map being an equivalence would imply that this one is an equivalence as well, because the map that sends an affine scheme to the map from this affine scheme to R is an equivalence between affine scheme and algebra. So yeah, and I know that this map here is not an equivalence because the fiber over 0 isn't it. And so let us prove this. So the idea is to present this type as a push-out. So here I will use the first piece of the affine cover. Say x is not 0. I use the y, and so here and here I use the xy in A2 such that the product of x and y is different of 0. So here I have a push-out. I have the map I, which is induced by the obvious map here. And so now I can apply the functor sending a type to the map from the type to R, and this will give me a pullback. And so all those pieces are affine, so I can simplify what I get. So from this, I get, so at the top, I have this one. It's here. I have this one, and here this is a pullback. Here I have an induced map like this. And so what I want to prove is that the map here is an equivalence. So to do this, I just need to prove that any element in the pullback comes from a unique polynomial. So okay, so let me assume, say, f and g such that f is equal to g in Rxy localized xy. So this is an element in the pullback here. So and so now I can do some algebra. So then I know that f is a polynomial like this over x to the n. G is another polynomial over, sorry, over y to the k. And I know that both are equal here. So now I have to unfold what this means. So why I end up with is is equal to x xy to the of xy. So I know that there exists an L such that xy to the L factor. So I just need to use the rules for when fractions are equal. And so I get fk yk by n dxy minus y. I get that all of this is equal to 0. And so now I have to use the fact that in a ring of polynomials, the variables are actually regular elements, because a polynomial is equal to 0 if and only if all its coefficients are equal to 0. And we see that this is invariant condition when we multiply by variables. And so if I have from this, I can get actually that yk dxy is equal to xn qxy. And so yeah, I started from f is equal to this, but here I see that f is actually divisible by xn, and similarly q is divisible by yn. So both were polynomials to begin with. Yeah. So yes. Yeah, and so to know that they are equal, I know that they are equal in Rxy quotient the localized, sorry, at xy, but xy is regular, so I know they are indeed equal. And so, so yeah, so that means that any elements here come from an element F. So indeed, I have an equivalence.
I agree with the conclusion, but I don't understand what you. I mean, when you say F equal G, yeah, I mean, why do you have XY? You have F equal G in Rxy localized xy.
Yes.
So this means yn pxy equal yk pxy equal xn qxy in the localization.
Yes.
And then you, so why did you divide by xy to the n?
Just to write them in a way where it's clear that they belong to
Ah, okay. Okay.
This thing,
Sorry.
which is like the map here, if you write it precisely.
Sorry.
Yeah, okay. Okay. Good. So, yeah.
Yeah, okay. So we know this map is an isomorphism.
Yeah. This one. Yeah, which was the claim I started with.
Mm-hmm.
So, yeah, okay. So this gives us an example of scheme that is not affine and that is still something we very much want to consider. So kind of is an example of why you would want to go from affine to any scheme. So now let's look at another example, which is perhaps a bit more traditionally minded than this one, which is very classical thing. So here, example given, open propositions. Are schemes. So let us prove this. So we want to prove a proposition, so that an open proposition is a scheme. So let you be an open proposition. Since we want to prove a proposition, we can assume that it is canonical. So say U is equal to F1 plus 0 or Fn not 0. And so here the candidate for the open cover is the natural. So we just send Fi different of 0 to U. This is an open proposition, so the cover is open. We know that this is indeed a cover because if we have an element in U, we know that one of the proposition hold. And so the key point is that this is affine, and this, as David mentioned, is just the spectrum of R localized at Fi. So yeah. Yeah, and so the remark is that not all open propositions are affine, and so we will see shortly why. But before I want to give a result where I don't want to present the proof because it's a bit technical, but it's still a very important result. We have a proposition scheme closed under sigma types. So I will spell out explicitly what it means. If X is a scheme and G goes from X to scheme, then the sigma type is a scheme. So actually, in the case of affine, you can prove that the sigma type is affine, and then you need to do the pieces together. But I will not do this in details. But so this is actually very useful property of schemes. And so, for example, actually using the fact that affine schemes are closed by sigma type. And say that not all open propositions are affine. So why? Because for the rise L2 minus 0, which is equal to the sigma type of xy in A2 so that 1 to 2 is equal to 0 would be affine, and we already saw that this was not the case. So here I have an affine scheme, so in particular a scheme. This is an open proposition, so I know it's a scheme, so I know that no, I mean, if this open proposition was always an affine scheme, then the sigma type would be an affine scheme, and this would be a conclusion. Okay, so that's an example. Another property that is interesting and that we can see as a sequence of this proposition is that schemes are stable under identity types. Okay. Yes.
Can you repeat the last argument? Why? How does it work? So,
So one thing that I didn't even write down, and maybe I should have, maybe that's why you're confused, is that if I have an affine scheme and a family of affine scheme indexed over it, then their sigma type is an affine scheme.
yeah, okay.
And so then my claim is if every open proposition was an affine scheme, this would be an affine scheme, and this is a contradiction.
Okay. Yeah, so it's not, you actually don't use this proposition.
No, and that's a bit of a confusing presentation, sorry.
Okay.
Yeah.
But it's called a remark and not corollary.
Yeah.
No.
Yeah. Okay. So schemes are stable under identity type. So let us assume x, y in x the scheme. Let ui be an open closure x by a affine scheme. Then we have that say that x belongs to a certain open UI. So we know that it belongs to one of them because that's a cover, and that's the definition of a cover. And so when x belongs to UI, we know that x equals y in x is actually equivalent to the sigma type of y belongs to UI and x equals y in UI. So because we know if they are equal, since x belongs to UI, so does y, and they are equal in UI because belonging to UI is a proposition. And conversely, if they are equal in UI, we know that they are equal in X as well. And so this here is an open proposition, so it's a scheme. And this here is an identity type in an affine scheme. And so we know that actually it's a closed proposition. And so it's also a scheme. Since schemes are stable by sigma type, we can conclude.
Sorry.
Yeah.
I'm slightly confused by the statement, because it seems to be schemes are stable under identity types says if X is a scheme, Y is a scheme, then X equals Y This was a scheme.
So that's not what I mean at all.
Yeah. So
What I mean is for all x, y in x, this is a scheme. Yeah, and for the equality type, this does not.
Yeah.
This does not hold.
Sorry, can you explain the last line here? I'm confused because why is 3 on the left-hand side but not on the right? So is it the same y on both sides morally? Okay.
Okay, I see your confusion. I will write this precisely. So, yes. So it's the sigma type of P, which is a proof that Y belongs to UI. And then you ask that X and this unnamed proof here, that what I could name Q, is equal in the sigma type of X, let's say Z in X, such that Z belongs to UI, which is equivalent to Y is equal to Y and B. That's what I should write precisely. And I know this is an affine scheme. I know this is an open proposition. And so conclude this way. Yeah, in practice, I would write it the way I did before, just because this is a lot to write down, but that's what you should write precisely. Yeah, and so these two properties together, the stability under identity type in this sense and under sigma type, actually what it means is that schemes are closed by finite limits. So, which is an important property of scheme and one of the reasons they are more convenient to use than, for example, manifolds in some situations. Yes. Okay. So now we will see an exotic example of scheme, just so you see that not every scheme looks super reasonable. This is what I want to tell them the first time.
Before you raise, have we used that it's a finite open cover yet and not? So why is infinite not allowed?
So it's not allowed in the way we set up stuff at the moment. If you were to use any type as Y, then things would go very badly, because everything would be a scheme, because you have that X is equal to like this, which gives a cover indexed by X. By 1, which is obviously affine, so you cannot use any type. But there could be extension. For example, here Y countable is probably reasonable, but I didn't check this in detail. The point is we don't, so far in the development, we don't really need more than finite, so we don't use more.
On a related note, I'm slightly confused about the definition of a scheme, because in the usual practice, you also require something more, right? You require they are coherent on the sections. So this affine cover of a scheme X is not in a classical algebraic geometry context. It is not just a cover, but you also require, if you describe harmonic sections, and there's kind of a co-cycle condition.
I don't think so.
No.
This is like a growing result, not the definition scheme.
It seems to me that in the traditional setting, you just use a cover like this as well without condition. I mean, since you use a cover, you know that on the intersection they will agree because they cover the same thing.
Because it is slightly like, because you say UI is affine, but in practice it should be like UI is isomorphic to some affine.
Yes.
And this isomorphism contains additional data, which you require on different pieces. These two isomorphisms do not contradict to each other. I mean, does that make sense? I mean,
No, it's not part of the data, but it's
So I
not
think-
part of the data, but I think you can't make sense of those code cycles. I mean, definitely you know what open, I mean, you know what open means, and then an open, and I mean, it's, you have a locally written space, and then you can ask whether it's, when you take a local piece of this locally written space, whether it's isomorphic to an affine.
yeah.
Locally written space,
Yeah.
and that's it, and they have no code cycle condition. I mean, you don't get one because you
Yeah,
can
but-
fix the isomorphisms.
Yeah, but you start with a local ring. That's kind of. But here we don't start. We start with an arbitrary type, right? You do not a priori know, like these isomorphisms, like different pieces.
So,
I'm
I'm not completely sure I understand your question. One remark is that being an affine scheme is a proposition. It's not an additional data.
Okay.
Because I can ask that simply that the canonical map
Okay.
and that this is finally presented. So it's a scheme in all of them.
I mean,
Sense.
one other remark might be that even though we don't have this sheaf of rings, it's kind of still there. We could look at maps into R like we do here, also for the whole space or own subsets. So kind of have a structure sheet.
Right. Okay. Yeah. Yeah. I understand. Thanks.
And I think that's also more a reason why it's okay to just restrict to finite eyes, because our affine schemes are made up from finite data. They are finitely presented. So and only just do finitely many things. So again, it's just finite, some kind of finite flow limit. And so if you want to, I mean, when one would like to have to have an infinite I, for example, countable one would at the same time like to replace finitely presented by something more general. Because I don't think it makes sense just to to restrict to finitely presented and then try to do it with any of them.
Okay. Yeah, that sounds reasonable. Yeah.
Continue on this. So, how will you prove that if X is the scheme and X is the set?
So, well, like this, I have this one available. So here I didn't use that the scheme was a set to begin with, but I know that this is an open proposition by definition of an open cover. And I know that this is a proposition because it's equality in an affine scheme. So I could deduce it here. Yeah. Yeah, but to deduce that in the set, you just need any cover by sets. So you know it's much more general, of course. Of course. So okay, so now I want to give
One more question. You said these are closed under finite limits,
yes.
but finite limits in sets or
What do you mean?
so
The limit in sets and the types is
the same. I don't know. It's okay.
Yeah, for limits it works fine.
It's okay. Yeah.
It works fine. Yeah. You never have to truncate. So yeah. One way you can see it is that it's stable by pullback because you can write pullbacks using sigma and identity type. Then
Yeah. Thanks.
Okay. Okay. So now I will give a more exotic example of scheme. So first I will present it really synthetically. So, example of scheme. Let U be an open proposition. Then the suspension of U is a scheme. So, so the suspension, it's what is called the higher intuitive type. We'll not go on the details, but the idea is that the suspension of the type X, it's the type that you build by having a north pole, a south pole, so 2 points in the type. And then for all points in X, you add a path from north to south. So for example, if you start with a circle, you will get a sphere because that's where the idea of calling those meridians comes from. And so when we do the suspension of a proposition, we know that what we get is a set. So it's like 2 points north and south. And for all proof of the open proposition, we equate them. So, for example, if the proposition is false, then it will be 2 points. If the proposition is true, then it will be 1 point. And so you have this family of types in between, and actually there are schemes. So this example from a classical perspective seems a bit surprising, maybe, but I will. Yeah, so let us prove this to begin with. So, so we look at the inclusion of the north pole in the suspension. So we want to check that the fiber of this are open. And actually, since being open is a proposition, we just need to check that the fiber over the north pole and the south pole are both open propositions. Over the north pole, the fiber is contractible. So it's open. Over the south pole, we have a property which is true for the suspension of any proposition, that this type is equivalent to U. So it's also an open proposition, and this is indeed an open piece. Of course, we have the same with the south pole, and the two together form a cover, because here again I want to prove the proposition that for any point in the suspension it's either equal to the north pole or to the south pole. And so for the north pole I know it's equal to I know that's equal to the north pole, so that it's in this part of the cover. The south pole, I know it's in this one, and I just need to prove that if U is inhabited, the two proof I get were the same, that this works out fine. And yeah, so those types are both points, so they are both equal to 1, which is indeed an affine scheme. And so this is an open, a finite open cover by affine scheme. So yes, so this example might seem a bit strange, but actually we can show that it's somewhat similar to something much more well known. So let's say the definition. We can define the sigma type of R in A1, so just an element in the base ring, and then the suspension of R different of 0. So this is the scheme. So because A1 is an affine scheme, so it's a scheme, and this just proves that it was a scheme. And so if we try to draw this type away from zero, it just looks like the line. Because when R is in front of zero, this proposition holds and the suspension is just a point. At zero, this proposition is false and we have 2 points in the suspension. And so infinitesimally close, we have those surprising type that are there. But so this is an example of a scheme that is not affine, and that is often called the line with double origin or the line with 2 origins. So
Usually it's an example from not separated. That's also the case for us.
yes, yes, indeed. So separated means that the identity types of a type is separated if their identity type are closed proposition. And so then you can show that affine scheme are separated, for example, and you can show that this here is not always separated because the identity type of the north and the south is an open proposition. And so similarly here, you can show that it's not separated.
Does this agree to the definition as a push out? Because you can define the line with your origins with a push out of 2 A1s with where you identify so 0.
Yeah, both agree.
This is the same thing.
Yeah.
Okay.
Yeah, both agree. And actually, that's if you want to prove that it is not a fine, it's easier to use the push out and then just do the same as I did here, basically. Yeah. Yes, so interesting example. So now let us look at a very important example of scheme, which are projective spaces. So we define the so-called projective spaces. So Pn is defined as the type An plus 1 minus 0, quotiented by an equivalence relation on this type. And so I define that X is equivalent to Y if there exists a lambda in R times. So R times it's the invertible in R. It's the same as the element of R that are not 0. And so there exists such a lambda such that lambda X is equal to Y. And so you can check that this is an equivalence relation. So this is the proposition, because here when I write exists, I mean the propositional truncation of the sigma type. And then you can show symmetry and so on.
But you can take sigma.
You can take.
I mean, it's unique.
Yes, yes, indeed. The lambda here is unique, so I could use a sigma instead. That's it will still be a proposition. Yeah. Okay, thank you. And so. Yes, so I think so I write x0 dot xn for the class of this vector in Pn. So for this to make sense, I need this element here to be different from 0, meaning I need to have one of the xi not equal to 0, because I quotiented an plus 1 minus 0 to begin with. And so there's a bunch of alternate ways to define the projective space. So we will not prove that they are equivalent, but I will give the alternative definition nevertheless. So one which is not so useful in practice, or at least that I didn't use in practice, but which is it's nice that we have it, is that you can define Pn as the type of lines in Rn plus 1. So rather than taking a non-zero vector and quotienting them by being collinear, you can define what is the line in Rn plus 1. Take this definition.
From the origin.
Yes. Yes. Yeah, one definition which is a bit, which requires more homotopy type theory to understand, but which is actually useful in practice from time to time, is that so here we have a set quotient, but if we look, we can see that it's actually the quotient of an plus 1 minus 0 by a reaction of r times. And so in homotopy type theory, whenever you have an action of a group on a set, you can actually give this will be a small remark on homotopy type theory that has nothing to do with algebraic geometry. So G is a group. Then G action are, the type of G action is so it's equivalent to the map from BG to set, where BG is what is called the delooping of G. So it's a type that is pointed and connected and such that the type of equality of the points with itself is G.
So here set, by set you mean 0 times, or?
Yes.
And the G action also sets, but.
So it's the action of G on sets. Here I assume that G is a set.
Okay.
I define this as the G action of set, the way you would expect, and then I have this equivalence.
Yes, this small remark, all algebraic structures in hot are sets.
Yeah.
That is all that is assumed.
Okay.
The G could act like a bias.
Yeah.
The G section is.
At least in this case, I'm thinking of a group, yes. Yes, and so we should have a map from BA times to set that correspond to the action by which I quotiented here. And actually, you can show or define, depending on which set of things, that BA times is the type of V in R module, such that we merely have that V is equal in R mod to R. So here we see that this type is pointed and connected. So it's pointed by R and it's connected because we look at points that are merely equal to R. And then you know that R equals R inside R module is type of, it's R times, because you know that maps of R module are linear and they are automorphism if and only if they multiply by something invertible. And so from this, actually, you can see that the corresponding action over there is the map from BA times to set that sends V to be n plus 1 minus 0. So this I will not prove. And then you can also show actually for any such action here, any such free action, that the quotient of the action is the sigma type of this element here. So from this, I mean, it's a sketch of proof that Pn is actually equal to the sigma type times of n plus 1 minus 0.
Sorry, but do you have to assume some very strong propositional resizing, because now P8 suddenly lives in a higher universe, right? If you don't have
A priori, but in fact you can show this. These like replacement principles.
If I were to define it like this, then what
I mean, it might look like a large type, but it's equivalent. I can show it's equivalent to a small type.
Yeah. Because we have the other construction.
Yeah, for example.
So far,
Huh?
That's all that would be.
Là, the equivalent is this equal to Pn is equal. The fact that it is equivalent to small sign plus Pn. Is
Because A star is small,
Yeah.
and then the looping is essentially small.
yes, so this type is actually equivalent to a small one. So I would carry out this construction like this. Yes. Okay. And so I have a bit of time left, and so what I will do is prove that projective spaces are schemes. And then I will stop. So say, well, projective space are schemes. And so here the idea is that we know that one of the coordinates is not 0, since the point we started with was n plus 1 minus 0, and so we just use each coordinate differently. So, for example, we have we look at the type of point in Pn such that xy is different of 0. So this is a map from Pn to open proposition. I have to check that this is well defined in the sense that for two equivalent elements of Pn, this proposition are equivalent, but this is the case. Because if two vectors are equivalent in Pn, then one is the multiplication of the other by an invertible element. And so I get here to multiply by an invertible element which doesn't change the proposition. So this is indeed well defined. I know that this is the part of an open subset of Pn because the fiber is just this proposition that is open. And I know that if I look at all the pieces for I equals 0 to n, I cover Pn. Because an element in Pn, I know that one of the coordinates is non-zero by definition, and so it will be in one of those pieces. And then what is left to prove is that this is an affine scheme. And so, yeah, what was the best way to? So yes, so we can show that this is equivalent to the element in Rn plus 1 such that xi is equal to 1. So, so the idea is that Yes, okay, so let me write the maps here. So if I start from x0 xn in this type, I send it to x0 divided by xi and so on. So I know indeed that the ETH coordinate here is 1 because it's xi divided by xi, and I'm allowed to do this because I assume xi different of 0. The other way, I just send x0 is sent to the class x0 xn. I know that the eighth element here is 1, so indeed it's different of 0. And one can check that this is an equivalence because we push it by this relation. And so now we just need to check that this is a fine, but this is actually equivalent to right. Yes, and I will stop the lecture here. Thank you.
I have a comment.
Yes.
This proof is actually formalized. I mean, we have this project of also formalizing what we do, and yeah, this is one we managed to do. But the project formalizing SAG is we have very little compared to what we have in paper.
Yes.
The statement that schemes are closed in sigma types. That's some sort of, do I think about it as some sort of descent statement? Because it works for all sigma values. It's not like you say, oh, it only works for basically flat morphisms or something. But is it some sort of descent?
I don't see it as descent, at least. Yeah, I really see it as stability by finite limits of schemes. I mean, part of it.
I mean, what it also gives you is that this equivalence between maps into a type and maps into the universe, you also have for schemes. So maps from, when you fix some scheme, then scheme maps into it are the same as maps from this scheme into the type of schemes. Some other way of thinking about it.
Yeah, but I feel one thing to when trying to understand this result, I think one very important point is that you have a map from X to scheme. So say X is the scheme. So here it's actually it's a map from X to the universe. You have just have a family of type such that for X in X you have is scheme. So let's call it P. You have is scheme P of X, where being a scheme is like there merely exists a cover by finitely many open. But here you can use Zariski local choice here when X is a scheme to get that you have a cover by open where the scheme structure is given from the open, and that's why it goes through in some sense. So maybe the fact that the sigma type is a scheme is more about how you define map from X to scheme.
But this predicate B scheme is still a proposition, or?
It is a proposition, so it's defined so as to be a proposition. So you say here, when I say there is, I mean the propositional truncation of the sigma type of this. Yeah.
So you said then, so I get a cover of X by Zariski local choice, And on the cover, I have a particular scheme lying over it. By the local choice. And these are then glued together as to form the segment type. Okay, yes, but that really sounds like the sentence again, right? So that is then some sort of descent.
So it could be. I'm not sure what you mean by descent in this context. I mean, descent is a word that is used a lot. So I'm not too sure what you mean.
If you have a collection of screws lying over the opens of your base scheme, then in good case you can glue them together to form a scheme. And in classical algebraic geometry, you need like conditions like pavely flatness of flipomorphisms. And here you can do it without any conditions. So I was wondering, like, why are there no conditions there? Or why?
Yes. So I think I understand your question, but the thing is, actually, there is a condition which is a bit hidden, but it's because when you look from map from X to scheme, since you're in the Zariski topos and you have Zariski local choice, you actually have some condition kind of hidden already, that the scheme structure is given up to Zariski code.
Okay.
So yeah.
Yeah.
So is there some other questions? Okay, so, thank you. Yeah, and so now we have